So thanks for joining us on this presentation. This tennis ball collecting robot, it was a collaborative effort between the three of us, me, Chris, and then Julius and Jose. And the objective of our robot is to look for an object. The simplest thing we can think of for the project would be a tennis ball, a nice green object which really stands out from an indoor environment. And we use a Raspberry Pi in conjunction with a camera that the Raspberry Pi Foundation actually produces and sells along with it in kit form. And we are using custom-made programs. Primarily, we're using Python to do the coding, along with another framework, Flask, to do a web interface. And we're combining object detection, and we are combining steering control and a distance sensor in order to also do object avoidance. And so on the next slide, to talk more about the hardware, we are using the latest generation Pi on the hardware. It provides a lot of firepower to get the job done. We also experimented with the third generation Raspberry Pi, but the processing was a little bit slower than we wanted. And a benefit of the Raspberry Pi is that the operating system has built-in tools for the image processing from the camera. And what we ended up using for the frame is an old RC car that I had found in a vacation home I was in. So it's hard to beat free for the components on the project. Didn't have a battery, so we ended up looking online for what's the latest and greatest, what's the new hotness, and batteries, and lithium ion is definitely a popular choice these days. So we picked up a 2 series lithium cell, and that offers voltages from a fully charged battery at 8.4 volts all the way down to about 6 volts when depleted. And that provided a more than zippy enough car for our project. And to talk about the software in the following slide, we ended up having to use an older Raspberry Pi operating system. They call it Raspbian. And then the second name, Buster, that's like the generation of the operating system. That's their previous one, where Bullseye is the newest. Buster uses a old style of programming interface, kind of like how there's Python 2 and Python 3, and there's some software incompatibilities between the two. And there's Raspberry camera, and then there's libcamera, which is kind of like what Python 2 and Python 3 are to each other, not quite compatible with each other. But we are using Python 3 to join many different software packages together. There's OpenCV, which stands for Open Camera Vision, and that's what we are using to draw on top of the camera feed. Things like draw a box around the object, and it helps us determine where the object is on the frame. And then there's TensorFlow Lite, which is the software that does the machine learning, and it's used to implement the object detection and the tracking. We're able to incorporate it with Python. And then Flask is a web framework that we use to view the information on a web browser for the car. Mainly, it was a set and forget sort of deal. That was the easiest implementation for us to do, but during testing, it's kind of like fighting a 5-year-old toddler that's running away from you. That's what the car ended up kind of doing while testing. And on the next slide, we have the design of the robot. That what we have, it was on the RC car, we just took away the plastic body of it. And on the left side, we have a 3D printed mount that the camera is on. And then there's the little gray ribbon cable that runs to the Raspberry Pi in the middle. We also have a battery that's connected on or just like pretty much rubber banded onto the robot frame. And that provides The whole voltage, all the voltages for the car. We have a buck converter right next to it, which provides 5 volts that the Raspberry Pi needs. And then the Raspberry Pi is able to generate 3.3 volts that the camera module needs and that the steering sensing board that's in the front needs. Kind of hidden in the middle is another board that has a few transistors connected together in an H-bridge configuration. And that's how we drive our motor, either going forwards or backwards. There are 2 different motors on this car. On the left side of the front, we have one motor which connects to a linkage to the 2 front motors or the 2 front wheels that lets the car move left or right. It kind of has the same limitation as a full-size vehicle, not like a Roomba style frame where it can move in place. This one actually you have to drive it forward while turning the wheel in a direction for it to turn. And so on the next following slide, we have a couple different alternative views of the vehicle. It has nice big tires for getting around smaller obstacles like pack of cards and any small Legos on the ground. But the camera is high enough on the ground to provide a good field of view for the environment that's in front of it. I have another RC car that was going to be our plan B in that little basket there, along with some other toys that I was using for testing. We just used a tennis ball as our object to detect, though there is an option for detecting other things as well. In our default software package, we're able to look at other objects like, say, a brush or a pen if we wanted to expand the project to look for something other than the tennis ball. And so I'm going to pass it off over to Julius to describe more of the features of the car.
Oh, I think it was Jose.
Jose, okay.
Yeah, I'll be speaking about a little bit more about what the camera sees and how it determines the object's position. So here we have an overview of what the frame looks like. Here we can see that there's 4 main parameters of what the algorithm determines. So there's the location of the object in the frame. There's the name of the class of the object belongs to. Something called the confidence score, which is how confident the algorithm is that the object actually is. For example, say, we're looking for a tennis ball. The confidence score will say, it's about 80% sure that it is a tennis ball. And there's also the number of objects on the frame. However, ours is just going to be 1 since we're only looking for 1 object. And on the right, you can see there's the status of different modules, I guess you could say. On the top right, it'll determine whether there is an object, if it's currently tracking, and if it acquired the object. On the bottom right, there's the robot speed, how fast it is going. Robot direction, it'll say either move left, move right, or down or forward. Later on, we have an example of what that looks like. There's the X and Y positions of the object and the frames per second of the video stream. We were able to get about 4 frames per second while the algorithm is running, which is actually pretty good. Here's the mechanism for determining the object tracking. Using the X and Y positions of the frame, the program will put a red dot on whenever it finds the object. And again, later we'll see in a video so we can see what that looks like. And it'll put it in the center of the object. We define what's called a tolerance zone. The tolerance zone is going to be a green square in the middle of the frame. If the object is in that, or if the object is in the middle of that frame, the algorithm says to stop. That meaning that the object has been found and the robot has moved enough to where it is in front of the object. To determine where the robot is going to move, we calculated what's called the deviation using the X and Y coordinates of the object compared to the center of the frame. The algorithm will determine these values and compare them to the tolerance. And here is an example, a video example. There's no audio, so I don't have to turn it on. A video example of what the stream looks like when the algorithm is running. So I closed the previous web page, and here I'm going to run it and open the web page. So this is what the stream looks like. You can see all those values that I was talking about earlier. Here the algorithm determines to move left because the object is to the left of the tolerance zone. Move right. And once the object is in the middle, it tells itself to stop. I personally was moving the camera with my hand because it wasn't actually mounted yet onto the robot. Again, it's in the middle, so it tells itself to stop. I moved it forward. Now the robot determines that it has to move backwards in order to get the object in the middle. And you can also see on the top right, it says acquired once the object is in the middle of the frame. It's also not working 100% of the time, but once it moves, it starts to kind of track again and determine where the object is. So that's why I'm moving the ball around. Right there, it acquired it. Again, it acquired, it's telling itself to move left. The information is also put on the command prompt. Okay. And to talk about a little bit more about how the algorithm determines the position of the object, here's my partner, Julius.
Thanks, Jose. The object tracking algorithm uses X and Y values to move the robot. The X value is the left and right direction, and the Y value is the front and back movement. The algorithm makes sure that X and Y values are less than the tolerance values. Next slide, please. Every time a new frame is processed, the X and Y values are calculated. If X and Y are less than the tolerance value, the robot will not move. If X is greater than and Y is less than the tolerance value, the robot will either move left or right to reduce the X. If X is less than and Y is greater than the tolerance value, the robot will move forward or backward. And if X and Y is greater than the tolerance value, the algorithm will check which either is greater and moves toward the greater value. This is our demo of the ball tracking robot.
This also has no audio, so.
So you can see the robot moves straight until it sees a set tennis ball on the right. In the first image, we have the robot in the starting position, and it will move straight towards the object until it detects a tennis ball on the right. And once the tennis ball is detected, it will turn to the right. And thank you for listening to our presentation. That is all.